Hello everyone, welcome back to my YouTube channel, Black Box Engineering. Sorry it's been a while, I've been getting over a bad cold for the past week or so. So I'm going to get back into the circuit development discussion, or playlist I guess. The next thing I need to talk about is what are frequency filters or how they're designed. So in a in the real world, to, like with all the different like radio towers and whatnot, along with in lab like experiment stuff, there are frequencies generated by transponders or transceivers that have no use in a particular application, or they're considered unwanted noise. Many modern devices filter out those specific frequencies using filters. So there's an idea of something called a first order filter. Typically that just means that there's one like exponent available in a mathematical equation. Like I think the format is like x squared plus some number times x plus some constant. So that's like a first order equation. And then it just, if you keep on adding more variables with more exponents, you just get into higher order equations. So that's a mathematical way to think about it. But in a more practical way, it simply means an inactive filter using a resistor capacitor network or resistor inductor network. Inactive means that there is no extra power being added to the system. So in this case, voltage can only drop due to physical loss such as heat or other forms of energy. These filters are usually used in conjunction with higher order or active filters to improve the overall effect of the filter. They'll have a more stable voltage output and then a sharper cutoff range. I'll get to that later. So anyway, so typically most people know about the RC high pass low pass filters. I don't usually use resistance inductance networks for filtering, but full designs do use a combination. It depends on the application, of course. So an RC low pass filter looks like this. This is my forum post on this I wrote a while back. So you've got an AC source here at some frequency, and then the resistor allows lower frequencies, and the capacitor basically charges and discharges the higher frequencies to ground so that the output doesn't see as much. So let me just get back to my webcam here. It does matter the values of the resistor and capacitor. Almost always the R value is chosen depending on if you want more voltage or more current. So R is also chosen so that the capacitor value comes close to a typical capacitance value. Sometimes it's not always feasible to get every single capacitor value because in the real world we don't have infinite capacitance values for capacitors. So C value is then calculated given the frequency one begins cutting off. The equation for cutoff is as follows. The cutoff frequency in hertz is 1 over 2 times pi times resistance times capacitance. So let's say if you wanted a 1500 hertz cutoff and wanted to use a 100 ohm resistor, the following capacitance would be calculated. So you take 1500 hertz equals 1 over 2 pi times 100 times C, solve for C, and you get 1.06 microfarads. So you can use this simulation software to show how this works. The way I did it is using an AC sweep, using 1000 data points from 1 hertz to 5 kilohertz. I will show you the actual simulator here because this might not make a whole lot of sense. So I'll try to explain it the best I can. So let me just create a circuit here. Forgive me, it's been a while since I've used this software. So again, getting over a cough. So I'm going to switch this to a AC signal. We don't need a sine wave because we're just using AC analysis. So we need, I'm going to say, let's let's aim for the 0 dB volt. Sorry, the 0 decibel value, which would be 1 volt. And we do not need any phase, so just a sine wave. So let's start it at 0. Hit OK. And I usually move this to the side of the voltage source. I need a ground, so I'm going to place one down here. I need a resistor. I just need to rotate it. I've forgotten all the shortcuts in this program, but that's okay. Most of the shortcuts in here. I need a capacitor, F3 for wires. Let me just get this out of the way so I know what to do. So across these, let's call them leads. This is going to be my output. So we set 100 ohms. Let me see. 1.06 microfarads. Hold on. I'll be right. No, not O. I meant U. Should be 1.06 U, not O. Because that's the the shortcut to that. So the next step here is to hit run up here. And then we need an AC analysis. We need a linear sweep. We need 1,000 data points. Start frequency is 1 hertz. And we can stop at, I believe, 5,000 hertz. Yes, 5 kilohertz. So 5,000. So it doesn't really look like there's anything happening, but that's because I haven't probed anything here. So let me just probe the output. So we get the same sort of looking graph that we have on the forum here. So let me just kind of run through what this means. Let me zoom in so that we can see what we're talking about. So in general, what's happening is we're starting at 1 hertz here and we're increasing to 5,000 hertz at the end. Of course, this is zoomed in now, so you can see that the voltage level is going to stay near the 0 decibel volts, so the 1 volts amplitude sine wave, and technically at around the 1500 hertz the 1500 hertz mark, which is right around here, we are going to see a pretty significant drop beyond that point. Now, ideally, we actually want cutoff to be closer to either 0 decibels or very nearly 0 decibels. So a RC filter is not ideal because we lose power here. In all actuality, this particular combination of parts here, I'd say that it's more towards the, like if you consider a 1 decibel loss, I'd say about 1,000 hertz approximately. Then it starts reducing quite a lot. We don't need the, sorry, just give me a second here. So this might not make a whole lot of sense, but there is a way to show you the same thing, by doing an actual AC signal to show you what's going on. So rather than doing this sweep, we're going to switch it over to linear mode. So let me just do that real quick. So the couple things that we need to change here, we do not need these things anymore. We need a sine wave. We need the voltage to be 1. We need the frequency. Let's say that it was 500 hertz just as a starter. Let's actually do a couple different samples to show you what's going on. So 250, we don't need any phase stuff, so this is clearly enough information here. We do not need, oops. Hold on. So that transient won't work on this particular thing now. So let's see here. I need several sample voltages here. So all right, so this example works. So there's a big cut there. I added a lot to the circuit here. All that I am doing is turning on and off different frequencies of the 1 volt signal to kind of show you what happens. So at about 1 second, for 1 second, it stays on. Yeah, 1 second in, we have a 100 hertz sine wave at 1 volt. And you can see that the amplitude is pretty much 1 volt. You can't really tell that there's any decrease here. At 250 hertz, again, it's going to be very close to the 1 volt. It's technically a little bit less. No, sorry. Before the filter, it's always going to be the full signal strength. I'm sorry. This is hold on. This is before the filter, before the resistor and capacitor, right? Between this and ground, right here, is the 1 volt signal. So this is the unaffected signal. If I measure the output, the amplitude is going to be very identical for the 100 hertz. It's almost no change. But on the 250 hertz, you now see, but it's very subtle, but it is less. But I need to add another thing. So all I'm doing here, let's say we want this to start at 4 seconds. We add a pulse signal here, a ground. We need this to start at, let's say 4 seconds. We need it to be on for 1. And we need the transient to now be, I don't know, like 8 seconds. So let's just close this. We've got an ideal switch here that is guaranteed to be set off by a 5 volt signal. So, sorry. So this is just a voltage controlled switch that we're turning on at a very specific time. Let's say that this is closer to the 1500 hertz level. Let's say 1000 hertz at 1 volt. And then we need to wire up the positive, or the positive side, I should say, to the to the input here. In an AC world, there is no positive side, but anyway, so if I run this, we should be having 3 different pulses, like so. And on the input, we've got our slower frequency, and at 4 seconds, we have the fastest frequency, and I believe it's at 1,000. Yes, at 1,000. Yeah. So, now we can see on the output side what's going on. So, let's just increase this a little bit more. And if I measure the output, and again, this is just across the capacitor. So if I'm just looking like I'm clicking one side, LTSpice knows that I'm measuring with respect to ground if I just click this node, but I am actually just doing this in reality here. And then let's compare it to input too, because we need both. I need to zoom out. It's a little hard to see what's going on. It's pretty hard to see the pink signal within the high frequency signal. But if I zoom in here, let's just keep zooming in. We'll see that the 1000 hertz signal has dropped significantly down to 0.8 volts because we are much closer to the 1500 hertz frequency signal that that we set up. If I include the pulses, it actually might be a little bit easier to see. So let's just add those in. It's just really stretched out because these are getting really fast. So anything past 1500 hertz is gonna reduce the amplitude incredibly fast. So if I added another signal here, let's say let's have a delay to 5.6 seconds here. So 5.6, and we want it on for 1. We copy the switch here. F3 to make a wire. F3. Let's say this was at, I don't know, 1700 hertz. Because now we're past the cutoff frequency. Okay, everything looks good here. Let's run the simulation. I want this to be in separate windows, sorry. So let's just get the pulses on the screen here. Zoom to fit because we need to see what's going on. So let's zoom out just one step further. So now we've got 4 pulses. So we've got the same the same input voltage levels, just increasing frequency as we go. The very last one is at 1700 hertz. So if I measure the output, which is in gray now, again I need to zoom to fit. You see that the amplitude is decreasing even further. We've gone to pretty much full signal strength, almost full signal strength, reduced as it's reaching the 1500 hertz mark, and then it reduces even more beyond the 1500 hertz mark. So the sine wave will keep on shrinking and shrinking and shrinking in size like this. And now let's just actually see how much we've actually reduced this by. So compared to 1 volt, it is down to point. Let's see, you need to add a little measurement thing here. Approximately 660 millivolts, so 0.62. From 1 to 0.62 is a significant drop. So yeah, if I just go back to my post, now you can actually make more sense of what's going on. For this particular example, I had a 14 decibel amplitude wave. The blue line here represents the full signal strength, and then the green line is the cutoff. So we're literally seeing the same thing, but in a linear fashion, where we see a representation of all those different sine waves, and that 1500 hertz mark, it really starts dipping down and down and down until it's practically zero. So so that's really all a frequency filter does. I just need to get back to my webcam here. So obviously that's a high pass filter. We're blocking higher frequencies. So sorry, low pass I should say. I always get them mixed up. That's a low pass filter. It allows lower frequencies and cuts off higher ones because it's low pass. So a high pass frequency swaps the capacitor and resistor around. Let's go to the post here. Instead of having a resistor here, it just swaps it out with where the capacitor was. This would have the same cutoff frequency, but now we would see a different effect where it blocks lower frequencies and allows higher ones. So this capacitor keeps charging up and charging up, but the thing is, because of how time constants work, if it goes fast enough, the signal will pretty much look like a full strength AC signal wave, because the capacitor is charging and discharging so fast that it doesn't matter anymore. So that's why you see the blue line start growing to the 1500 hertz mark, and it gets pretty much to that 0 decibel level. So let me just get back to the simulation here again. I can show you the linear version real quick. Sorry, I mean the frequency version. So let's just hide this for now. These can stay, because you'll see that the opposite thing happens here. Let's see. So I need to just swap these around. If I click the right tool. Okay. Come on. It won't grab onto the tool for some reason. So that's all that I changed here. And we're going to see kind of the opposite thing happen. So if I hit run, We got all our same pulses. But as frequency increases, we're going to see an improved signal strength on the output. So we see that at 250 hertz, it's practically nothing. Not exactly nothing, but if I just zoom in to the signal here, it is at 63 millivolts, so 0.63 volts. That's very tiny. That would be practically zero in many designers' eyes. At 100, sorry, I'm thinking about this wrong. This is the slowest frequency, so that'd be at 100 hertz. 250 hertz would be improved to oh, I have two cursors out. It would be improved to 163 millivolts. At 1,000 hertz, we are now up to 542 millivolts, so 0.5 volts. And this is the phase shift effect. If you're actually seeing that the output no longer lines up with the sine wave, that's because the capacitor is making it lag behind the initial frequency. That's the nature of filters. So and capacitors and inductors. I believe an inductor would lead it. So the sine wave of the output would be ahead of the input frequency. So so now we need to zoom back out to the 1700 hertz mark, and this is going to be much closer to the expected output. Again, it's not perfect because we're dealing with some losses here, and you'll notice that the sine wave gets much closer to the actual expected peak. It'll get closer to the phase shift that we see. So this one is at an output of 735 millivolts, 0.7. Technically, I don't think it actually ever reaches 1 volt with these active filters because of losses with the resistor and the capacitor. So it'll be 99.9% of the actual output input signal. So I'm just gonna delete this stuff real quick here and just show you the logarithmic or linear view, if you want to think about it that way. So we need advanced, we need 1, we need 0 phase. Sorry, it looks a little bit awkward, and then all you need to do is hit AC analysis, linear, 1000 data points, 1 hertz up to, I don't know, 2000 hertz, I'm gonna say. So the inputs can be a straight line, and then the output, I don't want the phase. the output is going to look like the inverse line as we saw on the forum post here. So if I add a measurement thing and I bring it out to the 1500 hertz mark, so 1.5 kilohertz, we're going to see that it really starts getting closer to the 0 decibel value, or the 1 volt value, and anything beneath that is going to be severely reduced, or the proper term is attenuated. So I think that's enough for the first part of the frequency filter stuff. I'm going to get into active filters next. I could have included it in one video, but I'm already at 42 minutes, so I hope this made sense to you. We'll see why active filters are much better than passive filters, because again, you can kind of reach a best of both worlds, because an amplifier or an outside power source can actually maintain it almost nearly to the expected voltage output, and then it can actually increase the attenuation curve, both high pass and low pass, instead of having this really gradual like curve, it's much sharper. So if I actually switch to my post real quick before I get into the weeds here, it'll look a lot more sharp. You can never have this golden yellow version because of how physics works. We can never have a perfect filter. But it'll start looking like the blue and green lines. It'll start cutting off really sharply at closer to the cutoff level that we want it at. So anyway, thanks for watching, and I'll see you in the next one. Hopefully that makes sense. If you want to see more videos on how to use LTSpice, that'd be cool too. So yeah, see ya.